All right, in this Big Ideas Algebra 2 tutorial, we're going to go through section 3.2, complex numbers. So by the end of this section, you'll be able to define and use an imaginary unit I, combine your complex numbers together, so that's add, subtract, and multiply, and then use that to find solutions and zeros of a quadratic equation. So the reason why imaginary units exist: there are situations where your quadratic graph crosses the x-axis twice. It gives you two solutions. It could cross once at the vertex, or it could cross 0 times and has no solution. Well, there are solutions, they're just not any real numbers. They're imaginary numbers. An example could be x squared equal to -3. The way that you would solve this is by taking the square root of both sides, and the square root of -3 does not exist. You cannot ever take the square root of a negative number and get a real number solution, because you can't square something and be negative in the opposite direction. So to overcome this, mathematicians created an imaginary number system where I is equal to the square root of -1, and then when you square both sides, I squared is equal to -1. So these are the two, think of them as keys or definitions of an imaginary number. We're going to be able to manipulate some equations that have a negative underneath the square root and just replace it with the letter I to help simplify it down a little bit more. So looking at just finding square roots of numbers that have negatives in them before we get into actually solving. So really simple simplifications of square roots. Square root of -25. Well, obviously you cannot take the square root of -25 because it's negative. However, you can separate this into two factors, where one of them is a positive perfect square of 25 and the other one is your I term, or the square root of -1. So pull out that square root of positive 25 and you can simplify that to 5, and then your root -1 then just becomes I. So the square root of -25 is 5I. Same thing with radical 72. You would want to separate that into the positive and then the negative. However, with this one, 72 is not a perfect square by itself, so you can then pull out even more perfect squares from that 72. So think of the largest perfect square factor of 72, and that's going to be 36, because you can actually take the square root of 36 and get 6. And then your root -1 becomes I, and then that root 2 just stays the way it is. Whenever you're simplifying things that have a radical in them to start, you don't want to then just take the square root and put it in decimal form. You want to make sure that it stays in root form. Then we've got -5 on the outside and then root -9 on the inside. Again, we're going to try and pull out the perfect square as big as we can, which is a 9, and then leave that -1 underneath the radical. Root 9 becomes 3, and then the root -1 becomes I. And then finally combining like terms with the -5 times 3 to get -15I. All right, combining like terms is exactly the same thing as you would treat your I as you would an X. So you cannot combine constant numbers by themselves with an I term. You cannot combine I terms with the constants. So you just need to find what's in common and then combine them together. So right now we have an 8 minus I in the first parentheses, and then a 5 and 4I over there in the second parentheses. Whenever you're combining them together, just bring your 8 and your 5 together to combine. I don't know why all of a sudden that it switched from a negative to a positive, but let's just assume that it was a positive to begin with. Here, up here, this is supposed to be a positive. So then you would take your 8 plus 5 to get 13, and then your I terms that get combined are the -1I and a 4I to get 3I. Now you can pull out the numbers and combine them like this, or you can just combine the numbers out in front, keeping that same term right here with the 3. Standard form means that you put the I term last. All right, you got 7 and 6I, 3 -6I. Again, combining the constants together, so you have 7 minus 3, and then your -6 and +6. Double negative right here makes this 6 a positive. So the 7 minus 3 is 4. And then you've got your 0i. Well, 0 times anything is 0, so this is just a 4, or those terms cancel each other out. Then we've got 13 minus 2 plus 7i, and then a 5i at the end. Again, group your things together so that they are with each other. So 13 and negative 2 go together, and that becomes your 11. And then you've got your 7i and then your 5i combining together to give you a negative 2i. Again, making sure in standard form your I is written at the end. So that's that. When you're adding and subtracting, again, combine the real parts together and then your imaginary parts separately. All right, so let's find this when we're incorporating some other variables. So you have some x's and y's in there as well with your imaginary parts. You're going to set the real parts equal to each other and then the imaginary parts separate. So your 2x is equal to your 10. That is your real part of the equation. Solve for x like you would normally by dividing by 2 to get x equals 5. And then your imaginary parts, you have negative 7i equal to yi. Your i's can get canceled out and you just have negative 7 to equal to y. All right, so using this in a real world situation. So you have an electrical circuit components that include resistors, inductors, and capacitors. They all oppose the flow of a current. So the opposition is called the resistance for resistors and reactance for the inductors and capacitors. Each of these quantities is measured in the term ohm. That's what this little omega is, the little symbol. The table shows the relationship between those components for the reactance and its contribution to impedance. A series circuit is also shown as a resistance of reactance for each component labeled. The impedance of a series of circuits is the sum of impedance of individual components. Find the impedance of the circuit. So a lot of this is just going to be application of your imaginary units. So right now, if you look at this graph over here to the right, notice that you have 3 ohms over here with the inductor, 5 ohms up here with the resistor, and 4 ohms over here with the capacitor, and then you have an alternate current source that is kind of keeping everything moving all the way around. So here's how we're going to solve this. Again, we're going to just replace those ohms with imaginary units. So you have resistor with a resistance of 5 ohms, so its impedance is 5. The inductor has the reactance of 3 ohms, like what I said earlier, so it's 3i ohms. And the capacitor has the reactance of 4 ohms, so then it's negative 4i ohms. Again, it's because it's impeding is negative. So when you combine all that together in order for this circuit to flow, you are combining 5 with 3i, negative 4i, and then setting that equal to 5 minus I. Again, combining like terms, 5 minus I is what is left over. Okay, multiplying is exactly the same way. So you're going to distribute whenever you have a single term on the outside, and then either foiling or putting in box method right there with 2 binomials. So distributing, you have 4i times negative 6. Again, treat your I just like you would treat with a variable x. So 4i times negative 6 is negative 24i, and then I squared. Remember, I squared does equal something, so you can simplify that to equal negative 1. That is a real number. So then you would just rewrite that as negative 24i and negative 4, writing in standard form. Foiling this, or setting it up in box method, you would multiply your first term to get negative 36, outer is 63i, inner is 8i, and last is negative 14i squared. Again, rewriting your I squared as a negative 1 and then multiplying those together. Now that you have a 36 and a 14, those are combined like terms to get your negative 2 out in front. All right, now moving on to the reason why we create imaginary numbers is to get these imaginary solutions. So x squared plus 4 equals 0. One of the ways that we've talked about how to solve quadratic equations is through algebra. So we're going to move this positive 4 over to the right by subtracting. Then take the square root of this x, and it is square root of -4. Now that we know that we can't take square roots of negative numbers and we can pull out imaginary units, you're going to take a positive 4 outside of that solution, take the square root of 4 to get 2, and your -1 becomes your I. Remember, always keeping the plus or minus because there are two solutions with a positive and with a negative. All right, now with 2x squared -11 equal to -47, again, we're going to move that 11 over to the right-hand side by adding to get -36, divide both sides by 2 to get -18, and then take the square root of both sides. The largest perfect square you can take out of 18 is 9. So you're going to pull the 9 out and leave the -2 on the inside. That square root of 9 becomes 3. And then that square root of 2 stays the same way it is. All right, finding the zeros of 4x squared plus 20. So if you graph this, notice how it does not cross the x-axis. You could solve this algebraically by setting it equal to 0, moving the 20 over to the right-hand side, dividing by 4, and then when you take the square root of -5, there are no perfect squares you can take out of this, so this just becomes plus or minus I root 5. Again, always making sure that we're keeping the plus or minus there as well. So you could still check this by plugging it back into your equation. Notice how when you square the I root 5, you get 5i squared. I squared is -1, so that becomes a -5 times 4 will give you your 20. Combine that together to get equal to 0. So it doesn't matter whether you're getting the real or the unreal solutions. You can still check your answer every single time.